The first speaker is Matthew David, and from University of Vermont, and the title is Word2vec Behavior, Morphology Facilities Grounding Language in Machines. Please.
So for the first time here, we show a robot that is able to hear language and execute the correct behavior, despite having never been trained specifically on this command. So here this robot was told to halt, and it executed lack of motion, despite having never been told to do this before. So why is this important? So today we can create complicated robots that can do things like autonomous driving and deliver packages. But these robots are specialized. If we ask this robot to deliver a package, to instead deliver it from a front door to someone's front desk, then the robot might need to open doors. And if we didn't train it specifically to go through doors, we might have a problem where the robot breaks through the doors. Now, we could manually intervene and tell the robot, don't damage anything. Deliver the package, but don't damage anything. This introduces a problem, though. If we want the same robot and the same controller to save people from a burning building, then we have a problem. The robot's been trained not to damage anything, and yet the robot needs maybe to break down doors in order to get the people and bring them out. So we want robots that can generalize and understand context and the subtleties of that interaction to understand what the right action for them to do is, and we need them to understand that context. So how can we do that? Well, this is a problem known as perverse instantiation, and it's been addressed a number of ways in the community and literature. And here we show that morphology can either resist, or some morphologies resist perverse instantiation better than others, and some do less well. So there's a strong connection between language, action, and morphology. So what does that mean? Well, if we show a motor homunculus, so that's basically a diagram showing how many motor neurons you have in your brain corresponding to different actions that you execute. So there's a lot of motor neurons that are used for speaking in our mouths, and in particular our lips and tongue, and there's also a lot of motor neurons that are used for controlling our hands. So that's roughly right underneath the part of the brain where you would normally be wearing headphones. So what's interesting, though, is that in the brain, when you put people in fMRIs and you read words to them like kick or lick, what we observe is that the part of the brain that would be executing these actions, part of the motor cortex that would be executing these actions, lights up. So the brain is simulating what it would be like to kick or lick something when it hears those words, even though it's not actually kicking or licking something. So computers that understand natural language have long been a goal of AI, and advances in neural network trained word embeddings can help advance us in that goal. So although this is not new, the idea of creating word embeddings was made much more accurate in 2013 when Google introduced Word2vec. So Word2vec, for those who might be unfamiliar, basically is the idea that based on the context around a word, we can predict what word is missing. So the cat blank on the mat, if we train a neural network to predict the word sat there, then we can leverage that to create a vector for each word in a language. Conversely, we could also take a current word and predict the words nearby in its context. But either of these approaches create the same thing. So intuitively, similar words that appear in similar contexts will be represented in this neural network the same way, and as such, they'll have similar vector embeddings. But the word embedding space is more than that. So if we look at the countries and their capitals projected onto two-dimensional PCA, we see there's this sharp divide between the countries and the capitals. And it turns out when you take a capital like Beijing, subtract out the vector for the country China, and then add in a new vector for a new country like Russia, the resulting vector is very similar to the vector corresponding to Moscow. In fact, they're the most similar vectors. So what this means is the vector space that we result in from creating the vector space in this manner preserves semantic information more than just how similar are these two concepts. So going back to morphology. So we send Word2vec vectors to our robots and have them understand language and generalize to new unseen language examples. So here we consider 3 base morphologies and a total of 6 variants thereof. And for each robot, we have a recurrent neural network controller, and this recurrent neural network controller has 5 hidden neurons and a number of sensors and motors dependent on the morphology. So in order to send the vector to the robot, here pictured in the forward, we send it into the auditory neuron and then propagate that through the hidden neurons prior to sending it to the simulator. So what does that look like? So prior to simulation, we take a vector, here, for example, backward, and we send the first element into the auditory neuron. That is then sent into the hidden neurons and allow them to update their state. Next, we send the next element, into the auditory neuron, and into the hidden neurons to update their state, and we continue sending it through all the elements in this vector. And what this does is it initializes the state of the hidden neuron layer, and as such, it allows us to have different vectors correspond to different initial states. We then take this initial state and put it into a robot. So here is a random robot controller, so i.e. random synapse weights, and we've just sent the word backward to the robot's hidden layer, and now we're going to transfer this hidden layer initialized into simulation. And we see that this robot leans over and then stays stationary, which is not surprising given that this is a random robot controller. So for each robot, we simulate it 6 times. We simulate it, we send the word, for example, forward to the robot's brain. We then send the brain to the simulator and allow it to execute behavior. We then record the behavior results, and then we reset the brain and send the next word. We repeat this for backwards, and then for words that mean stay still, we randomly pick 2 and, to use for training optimization, and then we hold out a third one for testing. And so basically, we can reward the robot and optimize it to do these categories. And what we have is we group the words together by forward, backward, and stay still objective. So when the robot is being optimized to move forward, we're optimizing it to maximize positive displacement in the x-axis. When the robot is optimized to move backwards, the same controller is optimized to do both. It is rewarded for maximizing negative displacement in the x-axis. And similarly, when the robot is optimized to stay still, the robot is optimized to minimize displacement from the origin. So here's a trained robot that we have just given the word forward to, as we talked about before. And we can see that this robot is executing forward motion. Similarly, when we give the word backward to this robot executes backward motion. So we have a population of 100 independent optimization runs. And for each of these optimization runs, we found a best robot controller. And for each of these best robot controllers, it was evaluated 4 times for the forward task and the backward task. And since these are both movement tasks, we can lump them together as a movement objective. And then we can take the absolute value of the total displacement in the x-axis and plot that in this green bar. And we see that the robots are able to learn how to move, given that they are displacing about 7 body lengths on average over these 400 different simulations. So next, we also train these robots to optimize their behavior for staying still when asked to do so. So here's a robot that's been the same robot as before, the same controller, and it was just told to cease, and you can see it curls up and then stops moving. And the reason why this is repeating, this is just looping, which is why it continuously contracts itself. Similarly, this robot was also given the command stay still, and we see that this robot does execute lack of motion when asked to do so. So similarly, if you look at the orange bar, there's a statistical difference between the green bar and the orange bar, where this is on a log scale, by the way. So the orange bar, the robot's basically not moving at all. And what we see is the robots are correctly learning how to move when asked to do so and not move when asked to not do so. So next we give them a new word they've never heard of that also means stay still. In this case, the robot was told to halt, yet it's never been trained on how to halt. And what we see is the robot executes the same lack of motion behavior, and that there is no statistical difference between the blue bar, which is how much the robot moved during testing, and how much it moved during training for lack of motion objective. So these robots are correctly generalizing to understanding what it means to stay still when given a new command they've never heard of before. So we talked about before that morphology plays a role in this. And we have some other morphologies. And we see that the spherical morphology also is able to understand how to optimize training. So in the green bar, it's statistically different from the orange bar. Thus, the robot was able to learn how to move when asked to do so and stay still when asked to do so. However, given that there's a statistical difference between the blue bar and the orange bar, and the blue bar being higher, we know that the robot failed to generalize to the unseen stop test synonyms because the robot is moving more during testing. So how do we know these results are correct? Well, we conduct the following control treatment, where we permute the vectors of the Word2vec vector space prior to optimization. So any semantic information that we talked about before has been lost now, and as such, we would expect the robots to be moving more during training than we saw during testing than we saw previously. And that's exactly what we see. So on the left 3 bars, we have the control treatment, which is the permuted Word2vec vectors. And on the right 3 bars, we have the control Word2vec vectors. And what we see is that during training, the robots performed very similarly. The 2 green bars are not statistically different. The 2 orange bars are not statistically different. However, the 2 blue bars are statistically different. The robot that was given the permuted Word2vec vectors is unable to understand what it means to stop when given a different word that means that. And you can see that the blue bar is quite simply higher than the other blue bar for testing. So some morphologies are able to generalize and some are not when given this Word2vec vector space as and for training and testing. So we also transferred simulation results to reality, and we have a physical platform that allows us to send Word2vec vectors to it and then execute behavior. And what we see is that when we transferred a simulation controller to reality, when given both forward and backwards, the robot moved forward. However, when given stop or commands that mean stay still, the robot did not move. And what we see thus is that although the robot is able to distinguish motion versus lack of motion and correctly generalize to the stay still objective, it's not able to distinguish forward and backwards. So in future work, we're interested in looking at more sim to real, so transferring from simulation to reality methods to more able cross our methodology to reality and see how well it works there. Also, our results have shown that morphology is critical in the ability of a robot to understand natural language. We show that the quadruped morphology is able to generalize to the correct previously unheard stay still command, whereas the spherical robot is unable to do that. And this suggests that there's some gradient. So if we imagine an inner and an outer loop, where in the inner loop, we're optimizing for the training, and then we can test on how well the robot generalizes, we can try and find morphologies that are able to generalize to these unheard commands. And as such, we can hope to align natural language with morphology and behavior in a better way. Thank you.
Thank you very much.